Hi, we'll be talking about our experiment that we did on finding the magnetic force on a wire. Before we talk about the experiment, we need the background knowledge about how magnetic field exert forces on moving charges in current carrying wires. The magnetic force is dependent on the magnetic field strength, current, length, and the angle between B and I. This is represented in the equation F equal to BIL sine theta, in which the strongest force occurs when the current flow and magnetic field direction are perpendicular. And if the current and field are parallel to each other, then there will be no force. This is because for a magnetic force to occur, there must be an interaction between the wire and the magnetic field. We have known that electric current means that the charges are flowing in a conductor. So if there is a current carrying conductor, then the charges will be moving due to the motion that each and every charge will experience a force. To find out how much force is on a conductor, we can find it through the formula F equal to QVB sine theta. This equation clearly shows that the force is perpendicular to the direction of the magnetic field and the velocity. So let's derive this equation further. The velocity vector is also the distance over time, where instead of the d we will represent with the L, where it shows the distance of which the electron travels. Then let's sub this velocity equation into the magnetic force equation, in which we will get the charge times 1 over the magnetic field. Then we can make Q over T, thus giving us the equation of the quantity of charge that flows past the cross-sectional area of the wire in a circuit, which results in having the equation to show that the force in the magnetic field on a current-carrying wire is equal to the current in the wire times the length of the conductor times the magnetic field vector. The image on the left shows a wire going through the magnetic field, where the X represents the magnetic field going into the screen. However, in the case where the magnetic field is going out of the screen, then we can draw a circle instead of an X. A current is shown to flow through the wire in the direction the arrow is pointing. This symbolizes a basic representation of the experimental setup. If the diagram shows that there is more wire, then that means that more charged particles are moving. Therefore, more magnetic force will be on the wire. This predicts the length of the wire and the magnetic force will be proportional. If you want to see the direction of the net force for the current flowing perpendicular to the magnetic field, then you can use the right-hand slap rule. The direction that the thumb is pointing shows the direction of the conventional current through the wire. The fingers pointing in the direction of the magnetic field and the palm points in the direction of the magnetic force. For this lab, we will be measuring the force on the current carrying wire, and hence we'll be investigating on the magnitude and direction of this force, which is dependent on 4 parameters: magnitude of the current, length of the wire, strength of the magnetic field, angle between the field and current, which we will conduct each experiment that shows the relationship between the magnetic force and the listed variables.
Now we'll be focusing on the first experiment that we have done. The aim of this experiment was to find the relationship between force and current. To do this, the force was measured at different currents. There are a few things that need to be noted, and one of them is that the magnetic field strength and length of conductor were to be kept constant. Secondly, the conductor should be placed perpendicular to the magnetic field. Lastly, the mass will be measured using the House centigram balance. The force was determined by measuring the mass of the magnets on the scale when zero current was applied and subtracting this from the measured mass value. The setup of this experiment consisted of having to assemble the main unit on the rod, and with the arms of the main unit you can connect to the low voltage power supply. You can connect the chosen current loop into the arms of the main unit, and this current loop is placed in the magnet assembly. The magnet assembly is placed on the balance. Note that the magnet assembly shouldn't touch the current loop. When the setup of this experiment was completed, we proceeded to measure the resulting force data. The supply was turned on and we initially set the current to 0 so that we can determine the change of weight, which in this case is the force in grams. This is a graph of the data obtained from experiment 1. The graph shows a gradual increase of the force when the current is increased. As we investigated the equation F equals IBL in the introduction, we have predicted that force versus current graph should give us a straight line, which suggests that the relationship between the current and the force should be linear. It shows that as the current through the conductor is increased, the magnetic force is also increased, suggesting that the current is directly proportional to the force. The vertical intercept of the graph shows the amount of current flowing through the system when the amount of force applied to the system is 0. For this experiment, it was observed that for the applied force to be 0, the current was also equal to 0. This agrees with the theory as for a force to be applied due to the magnetic field, there must be a current flowing through the wire. For this experiment, the magnetic force was investigated when the length of the conductor was varied. The aim of this experiment was to determine the relationship between the magnetic force and the length of the conductor. 4 conductor loops were used with lengths of 1.2, 2.2, 3.2, and 4.2 centimeters. The current was constant at 5 amps and 6 magnets were used. The conductor was arranged perpendicular to the magnetic field direction. The masses were measured for each of the 4 loops and the force was calculated the same way as in experiment 1. The mass when the current was equal to 0 was found to be 125.14 grams.
This is the table of force versus length, where it clearly shows that there is an increase in force when the mass is also increased. The graph of the force versus length shows that the magnetic force and length are directly proportional, which means that there is a force increasing when the length also increases. The slope of the graph shows that it is approximately linear, but shows a quite bit of error being present. The uncertainty of this graph is 1.03 plus or minus 0.67, which means that the error present could be due to the random error of measuring the length and also the measurement of the mass. The physical meaning of the y-intercept is that when there is no y-intercept, it means that no conductor length is present, thus making the force applied to be equal to 0. Since it is a linear relationship, it means that it is proportional between the length and the magnetic force. Experiment 3 is about how mass is measured when the magnetic field strength is varied. This variation is made when there is a change in the number of magnets. The current and length of the conductor is the only one that is kept the same. Like the previous experiments, the measured mass will help us calculate the force and the conductor is kept perpendicular to the magnetic field direction. The table of the magnetic field strength and the force shows the data for all 6 magnet mass when the current is 0 and when the current is 5 amps. Thus, the force is determined when the subtraction between the mass of the current being 0 to the mass when the current is 5 amps. The graph of the magnetic field strength versus force shows that it is directly proportional. However, the uncertainty is 0.19 plus or minus 0.11, which shows that there is also errors being present. Like the previous experiments, errors are quite similar. As such, There is a random error of measuring the mass by the eyes and the systematic error of the balance being sensitive to our hands as we are determining the mass. Proportionality expression that represents the relationship between magnetic force and magnetic field is F being proportional to B, where B is the magnetic field strength in Tesla.
This experiment was completed using the current valence accessory to vary the angle from -90 to 90 degrees. The angle was varied at 10-degree intervals, and the mass of the magnet on the scale was measured at each interval. The force in grams was calculated from this the same way as in experiments 1, 2, and 3 by subtracting the mass when the current equals 0 from the measured mass value. The current, magnetic field strength, and length of the conductor were kept constant throughout this experiment. This table shows the data obtained from this experiment where the angle is in degrees, the mass is in grams, and the force is also in grams. The graph of the force versus angle shows that as the angle increases from -90 to 90 degrees, the force can be observed to increase. The magnetic force initially increases slowly before speeding up slightly. The force increases almost linearly with the angle around 0, before slowing back down at a similar rate to which it sped up. The graph has a maximum at 90 degrees and a minimum at -90 degrees. The resulting graph of the data point shows a trig function. The trig function that best fits the data is a sine function because the data in the force versus angle graph shows a pattern that resembles a sine function. The line formed from the data points is shown to be close to linear around 0 and forms curves at an amplitude of approximately 3. The magnetic force is proportional to angle according to the formula F is proportional to sine theta. This agrees with the conclusion that the relationship between the angle and magnetic force of the above graph is a sine function. A large contributor to inconsistencies in the results were random errors, or errors that occur by chance and cannot be predicted. These errors were observed as when the experiment was repeated the same way, the resulting data obtained was usually slightly different. This could be caused by the sensitivity of the balance. It is also possible that the current loop was not always perpendicular to the magnetic field, resulting in possible errors in the experiments where angle should have been kept constant. An expression combining the individual proportionality expressions for the 4 variables is F is proportional to BIL sine theta. The magnetic force was found to be directly proportional to the magnetic field strength, the current, and the length of the conductor. The magnetic force was found to vary as a function of the angle between the field and the wire, which could be described as a sine function. This makes sense with the theory as the formula includes a sine function. The proportionality expression can be converted to an equation, F equals BIL sine theta. This equation can be used to predict the value of one variable if the other 4 are known.